Thanks everyone for joining us today. And our next session is on about machine learning engineering with TFX. I think we heard quite a lot in the previous sessions on the machine learning productions and deployment. So I'm really glad to have Robert to come here to speak more on that. Before we get started, just a quick logistic reminder. Again, for the Q&A, please post in the Q&A tab here. For other questions, chat, you can post in the chat. Again, the session is recorded, going to be available on YouTube shortly after the session, the event's done. Just search the AI Camp on the YouTube channel. And also I'm going to post the link to the chat. Make sure you join the Slack. We have all of our posts, update, announcement, slides, and videos, and also the lucky draws. Everything going to post in the Slack. So make sure you join the group to get all of the informations. And please to tweet the event and your learnings, and make sure to using the AIDevFest20 as a hashtag. We're going to have another lucky draw at the end of the event. It's going to be based on the hashtag. So make sure to tweet with that hashtag. So for our next sessions, it's going to be machine learning productions by Robert. Robert, he is a data scientist and a TensorFlow addict. He has a passion for helping developers quickly learn what they need to productive. He has used TensorFlow since the very early days and excited about how it is evolving quickly to become even better than it already is. Before moving to data science, Robert led software engineering teams for both large and small companies, always focusing on clean, elegant solutions to well-defined needs. Without further ado, let's welcome Robert. Hey, Robert, you can take it away.
Okay, thanks, Bill. Good morning or good afternoon where I am, or good evening, depending on where you are. We're going to be talking about ML engineering for production ML deployments, and specifically focusing on the open source platform from Google. So let's get started. So first, let's start with a thought experiment.
Sorry, I think you need to reshare your screen.
I need to reshare my screen. Okay, sorry.
Yeah, I probably took it over a moment ago.
Okay.
There you go.
Okay, so let me go back. Okay, can you see my screen?
Yes.
Good. Okay, so we're going to start with a thought experiment. And imagine that you're an online retailer who's selling shoes, and you're using click-through rates. Well, actually, you're using a model to predict click-through rates. And based on that, you're deciding how much inventory to order. And suddenly, the AUC on your model goes bad, but not on your whole data set, just on one particular part of your inventory, men's dress shoes. So the question is why? Why did your model suddenly go bad? I mean, you trained it, you tested it, you measured the performance, it seemed to be good, you deployed it to production. But more importantly, how do you even know that you have a problem? How do you know your model went bad? Well, welcome to the world of production ML. So there's a good possibility that you will find out that your model is bad after you order way too many shoes or not enough shoes. And that is not the way that you want to find out. So production ML is significantly different from ML in maybe a research or academic setting. There are business implications, and more than that, there's a life cycle to think about. There are easy problems where things change slowly, things like recognizing cats and dogs, or simple object detection with well-known domains, that kind of thing. your retraining of your model is going to be driven by maybe model improvements, changes in the software, that sort of thing. These are easy. More difficult problems, like the one we're looking at, are where things change, where in this case, things change maybe week to week as styles change, as the seasons of the year change. So you have declining model performance, you need to retrain your model, and that means you need labels for your data. So you need to establish systems to do labeling. Really hard problems are where things change very fast. So this includes ground truth, but also just your data that people are using. It's the data that people are using to make requests of your model. That's really what's important here. And that'll change, distributions will change, feature importance will change, a lot of things will change. And in some domains, it changes very fast. So if we step back and think about machine learning, we often focus on our modeling code. And that makes sense because, that's where really the magic is. That's where most of the research papers are written. When we get into production ML, we discover that there's a lot more to it that is required for success. And the modeling code that we started thinking about is maybe, well, we've measured it at typically around 5% of the code that you need to put a solution into production. And people have found out this reality the hard way. So here's a kind of a famous tweet now, where they developed a model in 3 weeks, and then 11 months later, it's still not deployed. So in production machine learning, you have all the normal challenges that you have with machine learning. You have to get labeled data. This is assuming you're doing supervised learning. Most cases are, but there are other things. Reinforcement learning is getting increasingly used, and of course, unsupervised. All the normal stuff. You want to minimize your dimensionality. You need to think about things like fairness. If you're in a domain like healthcare or financial services, rare conditions become very important. The data life cycle, maybe you don't think about that so much, but you certainly should. But we're putting a piece of software into production, so we need to think of all the same considerations as any software production deployment. So things like best practices, testability, safety and security. You have to account for the attacks that can happen against your model and try to detect them. So Google's done a lot of research in this area over the years. We've been doing production ML for a long time now at a very high level. And we've written a lot of research papers on it. These are all great. I encourage, if you have time, go take a look. So what now? We have all these challenges. What do we do? Well, Google's answer has been TensorFlow Extended, or TFX. And TFX originally started as a platform for Google to use, because we put a ton of ML into production across Google, actually across Alphabet. And we needed a strong platform to do that with. And there wasn't one available. So we created TFX. And a couple of years ago, we open sourced TFX. So now it's available to not just people inside Google, but to our partners as well. And we're seeing increasing adoption. This is just a few of the people who are using it. An interesting case is Twitter, because Twitter actually had a significant investment in Torch. And they went out a couple of years ago and did an assessment to see, should we continue to build on Torch, maybe move to PyTorch, or should we move to something else? And the something else that they chose was TensorFlow, largely because of the ecosystem, including TFX. So at a high level, this is a TFX pipeline. On the top, you have tasks that you're trying to do. In the middle, you have libraries that support performing each of those tasks. And in the orange, you have components that form a basic TFX pipeline. Now, this is just where you start. You're going to add to this and change this based on your needs. So you'll create your own components, your own custom components to do the things that you need. But at least to start with, you have a fairly good selection of components. Looking at it a little differently, there are some horizontal layers that are important. So the configuration framework, the DSL, job orchestration, and metadata especially becomes very important. So this is a different view of that same pipeline. This is I call this the hello world of TFX. This is sort of the starter pipeline that you'll get when you just install TFX. So on the left, we're ingesting data. We pass through these components, and we'll talk about each of them. And then on the right, we're deploying to a number of different deployment targets. So could be a server farm running on TensorFlow serving, could be a mobile application running on TensorFlow Lite, or a JavaScript application running in a web browser or in Node.js or some other JavaScript environment, or maybe you're just saving that model in something like TensorFlow Hub to use later for maybe transfer learning or generating embeddings, something like that. You can deploy to all of those in a single pass through your pipeline. So we sort of touched on components. Let's dive into what a component is. A component is made of three parts. There's a driver, executor, and a publisher. The driver and publisher are largely boilerplate code that you probably won't change. You could, but you probably won't. The executor is really where you will do your work. It's what makes different components different. So the driver extracts the input that the component needs. The publisher takes the result of the component and puts it into metadata. And the executor performs the work. So looking at it slightly differently, we have a metadata store. And except for the very beginning of the pipeline where we're ingesting data from some data source, all of the input is going to come from artifacts that have been produced by other components. Actually, there is another exception to that too that we'll talk about later. The component does what it does. It has a configuration and for many components, user code. And then it puts its result back into metadata. That happens over channels, input channels and output channels. And that's how components communicate. So you have a upstream component that produces a result, puts it into metadata. Components that depend on that result or that artifact then pull it out of metadata and process and put their result into metadata and so forth. So to do this, we need some orchestration. And TFX is open at the orchestration layer. So if you have a different orchestrator, you can add support for it. Out of the box, TFX supports Airflow, Kubeflow, a interesting version of Apache Beam, and an interactive context. So we'll talk about those a little bit. But at the end of the day, you end up with the same structure, the same directed acyclic graph or DAG. It's just the tool that you're using to orchestrate it is different. You also can run an entire TFX pipeline inside a notebook. So this is pretty handy when you're developing your pipeline or trying to debug it or making changes to it. You can just run everything inside a notebook. And in that case, the orchestration is done using an interactive context and just stepping through the cells in the notebook. All right, we've also touched on metadata a little bit. Let's dive into that. So what's in the metadata store? Well, there are artifacts, and artifacts have properties. So things like trained models are artifacts. Data sets and data set splits and spans are artifacts. Results of metrics and so forth are artifacts. Checks on the model performance are artifacts. These are, schemas are artifacts. There's a long list of of the artifacts that are produced. Also, those artifacts are grouped into execution runs. So I can look at an individual artifact, but I can also look at all the artifacts in that run of the pipeline because they're grouped together. They're linked together. So that allows me to look at the provenance of artifacts. And for things like interpretability, explainability, fairness, it's important to be able to say this artifact was produced by that component, which took that artifact as its input, and so forth, back to the original data. And that's what the metadata allows you to do. So for models, for example, you can find which data a model was trained on. You can also use this as an analysis tool to understand your training and model results. So I could, in this case, I'm comparing two different model runs. They could be months apart. I could be comparing what I did today with what I did 6 months ago and trying to understand why it's different. I can also avoid running components when I don't need to. TFX is designed to handle large data sets because we handle large data sets in Google. And if I don't have to run a component, which could take hours or even days, I don't want to run it. So if the input to that component has not changed and the code for that component has not changed, I just want to pull the previous result from cache. I also, if I'm just training my model, I want to warm start the model if I want to just run it for some more epochs to train it. I don't want to have to start over from the beginning. A lot of these components use Apache Beam to do distributed processing because, again, we're dealing with, or potentially dealing with, we certainly don't have to be, but we're potentially dealing with large compute resources that are required in large data sets. So what is Beam? Beam is an abstraction layer on top of any number of distributed processing frameworks, including Spark and Flink and Google Cloud Dataflow. There's also a very convenient framework that it runs on, the local or direct runner, which I can just run and often do on just my laptop. So I don't have to have Flink or Spark or whatever installed. I can just run everything on my laptop. So Apache Beam supports a number of different distributed processing frameworks, including that local one that we just talked about. And there's a number of SDKs for different languages. So using those SDKs, Beam takes operations and the SDK for Beam in that language, translates it into the native API for those distributed frameworks, and a result is produced. So looking at it a little differently, I have a TFX component. So for example, when I'm generating statistics across my entire data set, I'm running a component. The executor in the component is going to use Beam. It's going to send a Beam pipeline using the SDK to Beam. That is going to get translated and run on my cluster. And a result is produced, which gets sent back to my executor. So if I have a large amount of compute resources that are required for whatever I'm doing, this is how we distribute that processing across a cluster. But that cluster could be different for different teams. I could be running it on Spark and then walk it over to a different team that's running on Cloud Dataflow, and I don't have to change the code. There's portability. So at the beginning, we talked a little bit about the standard components. Let's go through those so we understand what they are. Again, this is the sort of the hello world pipeline of TFX. So starting at the beginning, we're going to ingest our data using ExampleGen. And there's actually a list of different data sources that we can ingest from, and you can add your own as well. But ExampleGen is going to pull in the data. It's going to do as many splits as you need, probably at least training and eval. It's using Beam to do this. And it's going to produce an output as an artifact that is actually a TF record file that contains TF examples. The next component is StatisticsGen, which calculates statistics across our data set. So this is the part of the ML development process where we're trying to understand our data and look for problems. So there's some visualization tools that come with StatisticsGen. It uses TensorFlow data validation to perform its tasks. And these visualizations help us understand, individual features and the characteristics of them, including a histogram of it and looking for missing values, that kind of thing. The next component is SchemaGen, which tries to calculate the schema of our data. So what are the types of our data? And for categorical features, what are the valid categorical values for those features? Sorry. ExampleValidator is the next component. It's going to take both of those results and look for problems. So it's going to look for things like, feature values that are the wrong type, maybe a float instead of an integer, or categorical values that are either wrong or just occur so rarely that they could be wrong. ExampleValidator uses the schema from SchemaGen. So you want to make sure that you've looked at that schema and applied whatever domain knowledge you have to make sure that it's correct. The next component is transform. So transform is where we do our feature engineering. And the code for transform could be as complex as you need it to be. Because feature engineering can, as I'm sure you know, can be quite complex sometimes. So things like, generating embeddings or doing PCA or something, you can do a lot of different kinds of feature engineering. It's using Beam to do that because there's a substantial amount of work, or there can be anyway. So distributing it across a cluster is usually a good idea. One of the things that transform does is produce a TensorFlow graph. That graph expresses the feature engineering that you want to do. And that graph gets prepended to the model that you train. So it's the input stage of that model. So wherever you deploy that model, you're going to do exactly the same transformations. So you're going to use those transformations when you train the model, and exactly the same code when you serve that model or use it in a mobile application or what have you. So you're going to write that code once, and it's going to be used everywhere you deploy the model. So there's no opportunity here for training, serving, skew, where you are trying to duplicate the same thing, maybe on 2 different platforms in 2 different languages. The next component is trainer, and trainer trains your model, as you might expect. So it's doing TensorFlow training. I should actually add that there is some support currently for other frameworks besides TensorFlow, and we're adding more as we go forward. So trainer is, the configuration for it is fairly straightforward, things like the number of steps. The code is going to be your TensorFlow model. And you have TensorBoard that you can use to try to analyze your training process and understand how to improve your model, including comparing your model that you just trained with a model that you trained at some point in the past, maybe months ago, to try to understand the difference as your model evolves and as your data evolves. Tuner works with Trainer to do hyperparameter tuning. So it's doing exactly that. It's trying to find the optimal values for hyperparameters for your model. Evaluator is going to evaluate the performance of your model. And it does that not just across your entire data set, although it will do it across the entire data set, but more importantly, it does it at a deeper level, looking at individual slices of your data, which is important. But it also requires some domain knowledge. So based on the domain that you're working in, those slices will be different. In our example from earlier, we have shoes, and one of those slices would be, men's dress shoes versus women's dress shoes versus men's casual shoes, and so forth. So if we wanted to catch the problem with our model performance on men's dress shoes, having those slices would be important, because the top level metric might have looked just fine, but that individual slice, which was important to our business, performed badly. And Evaluator helps you do that. Evaluator also looks at a comparison between the model that you already have in production and the model that you're training now. Because if your model that's currently in production is better than the model that you just trained, you don't want to push this new model to production. You want to wait until you actually have a better model. And Evaluator helps you do that. And then along with that, there's some visualizations that are provided to help you understand the performance of your model, looking at it in different ways with different slices to really help you analyze the process. The next component is InfraValidator, which tries to deploy your model to a kind of a shadow production environment and make sure that it can actually be deployed. So I don't know if you've ever had the experience of trying to run a model and then you try to run it on a different system and you discover that you don't have enough GPU memory. Things like that become a problem if you're actually doing that in a production environment. So InfraValidator helps you avoid those kinds of problems. If both Evaluator and InfraValidator have blessed the model, meaning that it's better than what you already have and it will run in production, then Pusher goes ahead and pushes it to your deployment targets. And those are the same things that we looked at earlier, serving and Lite and JS and so forth. We also have bulk infer. So if you're just going to run a big batch of inference, you could use bulk infer to do that. So this is it's a good utility to have for that sort of use case. Okay, there's one other little thing here. So we talked about components, but we didn't mention what are called nodes, which actually are pretty important. So let's take a look at those. Pipeline nodes they're special purpose classes. They're not components, but they're used for performing advanced metadata operations. So for example, if you want to import some external artifact and put it into metadata and use it in your pipeline somehow, you can use a pipeline node to do that. Or if you want to perform a query of your metadata and use that somehow, you can do that with a pipeline node. So there's an importer node to do what we just talked about, pull an external artifact into metadata and then probably use it in one of your components. And there's a resolver node, which is used to query metadata. In this example here, we're looking at the latest artifacts of a particular type. So we want the latest outputs from ExampleGen, and we want a list of 5 of them. So it's those sorts of queries where we're going to try to use that result somewhere, and we can do that by using a resolver node. And there's 2 current types of resolver nodes, the latest artifacts that we just looked at, and also the latest blessed model. That's used by Evaluator, for example. There's also been recently some more advanced capability to support TF Lite that has been added to TFX. So we've been able to train models for TF Lite for quite a while, but we tried to improve some of the operations because TF Lite, as you might know, has some specialized things that it does to try to optimize models. So now we do some of that within TFX pipelines if you decide to take advantage of that. So here's an example of the kind of code. It's really a fairly small set of things to do. So there's a signature and a tensor spec to take a look at. And we're going to pass that when we do model save. As you can see, it's really not much code, but this will help improve and optimize the model for TF Lite. And we do that with a rewriter. So there's a rewriter factory, and we're going to create a rewriter, and we're going to use that with TF Lite to rewrite our save model. And we need to still do evaluation of it. So we add a couple of things to our Evaluator component to make sure that it evaluates a TF Lite model correctly. Okay, so now we've gone through the standard components, the ones that you get when you do an install. Let's talk about how to create custom components. There are three types of custom components, or three ways to create one. At the end of the day, they all look the same once they're created, but when you create one, you can do it either using a Python function, or you can wrap a component, wrap a container rather in a component, or you can take existing components and just extend their classes. You use a custom component exactly the same way you use a standard component. It fits in the pipeline. It is orchestrated in exactly the same way. So for a Python function-based component, I take a Python function, I decorate it, I add some annotations to the arguments for it, and I'm ready to go. Very simple. For a container-based component, I'm gonna, I need to identify where to get that container, and then I wrap it in one call, and add some arguments for the standard artifacts, and I'm ready to go. I also have a command that I'll run from the command line when I start up my container. And extending the existing components, usually what that means, although you can do a fully custom component if you want to make changes to the driver or publisher. I don't think I've ever seen anybody do that, but it is possible. Most of the time, you're just changing the executor. So you're going to just extend the executor class and do something a little different. So you have all three ways there to create custom components. TFX also runs on Cloud AI Platform pipelines, which is available today. So at a high level, this is what that architecture looks like. We have Tensorflow, and Tensorflow is running in TFX. TFX, in turn, is running on Kubeflow pipelines, which is running on Kubeflow on the Google Cloud using the Google Kubernetes Engine, or GKE. And then there's a whole long list of services, including managed services, that you can leverage in your pipelines. Looking at it a little differently, this is the TFX pipeline here running on the TFX SDK, which in turn is running on the KFP SDK, which is running on GKE. It's going to be using the KFP orchestration, so that'll be using Argo. We have a bunch of GCP services that you can leverage. You also have a Jupyter Lab environment, which you can use to develop and monitor, and analyze your pipeline. At the end of the day, though, it's exactly the same pipeline. It's just running in a different environment. So that's TFX. There's a list of standard components for you to start with. There is flexible orchestration and metadata, and you can extend and build that pipeline to be what you need it to be with your own custom components. Here's our website. If you haven't looked at that before, I encourage you to go take a look. And here's some resources to help you get started. And with that, I think I'll break for questions.
Great. Thanks, Robert, for the presentation. And I think we have a couple of minutes. I think we have a few questions in the Q&A. Are you able to click the Q&A to look at the questions, or you want me to read it to you?
Yeah,
are
these all, do you know where, okay, let's see, some looks like it's for Carl. Which is the first one for me? I guess it's
if you refresh it, it should be like only you can see the questions for you. Oh, you see all of them?
So the last one I see is at 131. I think this must be for me.
Yes,
so,
I think from the 120, 124, that one is for you, Kuma.
So I see there's one at 103, it's saying overfit, and another one saying data changed. And then drift, I guess. These don't sound like questions.
Okay, you know what? Let me probably read it to you. Maybe it's easier. I can see all the questions.
I'm looking at the chat. I'm sorry.
Oh, okay, yeah. Click the Q&A. Yeah, look at the Q&A.
Okay. Yeah, user error. Okay. Do we get any sort of swags or badges? Not for me. What's the difference between Metastore in TFX and Feast Feature Store in Kubeflow? So the metadata store that's used in TFX and actually also in Kubeflow pipelines is for storing metadata. A feature store is for storing input data. So those aren't artifacts that are used within the pipeline. They're inputs into the pipeline. And the Feast feature store is an open source feature store that can be used in Kubeflow or TFX or whatever framework you want. It's not really specific to a pipeline or framework. So hopefully that answered your question. How to do distributed training with trainer. Can TF distributed be used? Yeah. So distributed training is sort of an ongoing development currently. The parameter serving style of training is currently supported, and we're working on the other distribution strategies. Let's see. What is the most common orchestrator used nowadays in production, Airflow or Kubeflow? That's an interesting question. I would just guess that it's probably Airflow, but I see a lot of Kubeflow too, and it's really anecdotal. We don't have any good numbers to look at to say which is actually more common. I see both. What I tend to see is Airflow used in smaller teams, working with smaller data sets and smaller models, and Kubeflow used more when people have a large enough team to support a Kubernetes installation, and they need that processing power. Is TFX available on GCP? Yes. So TFX is available as part of AI platform pipelines today. It's also, of course, I mean, you can always start up a GCP VM and install TFX as well. Or for that matter, you could start up a GKE cluster and deploy on that. So there's a number of different ways in GCP to run TFX. Including Cloud Composer, actually. If you're interested in Apache Airflow, Cloud Composer is a managed version of that. Do we get any sort of, okay, can you please share the last slide resources? So the slides were uploaded to the website. So hopefully you have access to that.
Yes, we're going to share the slides later in the Slack. So we just for the last questions, I see it's in the chat. Say, can the model determine any bias in the model or in the data?
I'm sorry, I didn't quite follow.
It's in the chat, the last one in the chat. Can the model determine any bias in the model or in the data? I'm not sure about the questions.
The model, okay, so the model only does what the model does. You give it training data and you train it, it only knows about that. It's not going to detect bias. Where you detect bias is in using TensorFlow data validation or TensorFlow model analysis. So you can do that within the pipeline in the StatisticsGen component. You can write your own custom component to use the libraries to do that, or you can do it outside the pipeline as well. But the model itself is not going to detect bias. It'll be affected by bias, but it's not going to detect bias. There's also, if you're thinking about bias in terms of fairness, there is the fairness indicators tools that are great for trying to analyze that kind of bias. And so I encourage you to look at that as well.
Okay.
Also on Google Cloud, there's the explainability offering as well.
Okay, great. Thanks. I think we are out of time. Again, thanks a lot, Robert, for the great presentation and the insights on the TFX, and also for the Q&As. We're going to take 2 to 3 minutes break while we are getting ready for the next speaker.
All right. Thanks.
Thanks. Bye.